Hello, my name is Varun, and today we're going to evaluate the different resource allocation policies on the Kubernetes Container Management Framework. We're going to look at the Kubernetes native scheduling policy and compare and contrast that with the DRF or Dominant Resource Fairness policy. We're going to run a couple of workloads and we're going to see how well they perform on each policy. We're going to monitor the CPU and memory utilization using a tool called Grafana, and we're going to measure how long it takes for the workloads to complete on the respective resource allocation policies. So let's take a look at our demo setup. For infrastructure, we have Kubernetes, Docker, and Amazon Web Services. And for the policies, we have the DRF versus the Kubernetes scheduling. Let's get started and set up our AWS cluster, which will help us run our Kubernetes tests. As you can see, Kubernetes manages the AWS cluster using its script, which creates virtual private clouds, storage, and all other resources required to run a cluster. And it configures all of this by running a script. This allows Kubernetes to take complete control of provisioning and destroying AWS resources, which again proves to be its strength. After doing this, we're going to set up a hosted network file system which allows the memory intensive workloads to get the data required for their workloads. And to do that, we're going to set up an NFS drive or a network file system drive on Kubernetes replication controllers. But to start, let's create a persistent volume on Kubernetes by running these scripts. These scripts have the configurations of the network file system that will be used by our workloads. After creating a persistent volume and a persistent volume claim, it can be configured to be used with our memory workloads, which is what requires a big data set. Having done that, let's now evaluate the native scheduling policies of Kubernetes. To start off, we're going to create some replication controllers and pods. And we do that using the kubectl create command, which you will see multiple times during this demo. So we're going to start by creating a Spark master node, and by creating a Spark worker controller, and by using a service to connect these two workers. With the help of the master and the worker, we can run our workloads. As you can see, we have a replication controller set up and ready, and we have the individual underlying pods ready as well. So let's get started and run our first workload. We're going to start with the Monte Carlo financial estimation workload, which is a CPU intensive workload. As you can see, we'll be using PySpark to do this, and we start this by using PySpark. And here we are entering the commands required to run the workload. As you see, there are functions that utilize the Monte Carlo financial estimation algorithms, and the key thing is the term, which is what defines the length of the workload and the complexity of the workload. The larger the term, the larger the computation. And this is the resource utilization. As you can see, CPU utilization is spiking and is trending upwards in comparison to memory usage, which is at much lower. So this is a CPU intensive process, and that is what is being demonstrated here. And as you can see, it just keeps on spiking. Now, let's try using the Monte Carlo financial estimation and k-means clustering together, thereby combining a CPU intensive and memory intensive workload together. As you can see on the screen, we're running both tasks side by side so that we can stress test the cluster to check how effective the native scheduling algorithm of Kubernetes is. So we're running two instances of Spark masters and workers, and now we are running the respective commands. Soon you will see the CPU and memory utilization of these workloads on Grafana. As you can see, even with both workloads, we're hardly hitting 800 millicores, which is less than 2 cores of usage to actual virtual CPUs on the AWS cluster, which goes to show there's poor utilization, and also goes to show that the running time of both workloads can be significantly reduced if the CPU and memory usage by both workloads were increased. And that is what is the problem with the native Kubernetes scheduler. To address this, we have built our own implementation of the DRF scheduling algorithm. To do so, we start off with a custom Python script, which allocates resources for the replication controllers based on the DRF algorithm. As you can see here, you can run the script and define how much resources each workload will need. Then, using the script, we will be able to define, by complying with the principles of DRF, what resources each pod or each container will get. As you can see, the resource files have been created, and now we will be creating the individual containers, pods, and replication controllers that control them. And soon we will run both the workloads. Now, let's run the Monte Carlo financial estimation and the k-means clustering algorithm together and see what the results are. As you can see, we're trying to use as much of the CPU resources, and to start off, we see in a matter of few seconds that our CPU utilization is already above 1.5 cores. It's at 7 cores right now, which is almost the max capacity of the entire cluster. The same can apply for our memory as well. Similarly, we also see that once the CPU intensive workload is finished, the spike has dropped. This is because our CPU intensive workload has finished under such quick time because it has been very effective. Similarly, the memory usage has also gone down after the workload is completed. Now, this is the great part of DRF based scheduling. DRF based scheduling allows us to overcome the nuances of Kubernetes native scheduling, which creates temporary unfairness to promote overall efficiency. And this is overcome by using our DRF hard allocated resource allocation policy, where thereby increasing overall efficiency of big data workloads on our system. It's been a pleasure demonstrating this project to you. Thank you very much.